Okay, so let's take the equivalent problem in the electric case for a charge and an electric field. So imagine you have a charge, a positive charge at position 1, and you let it go. And of course, when you have a positive charge and the electric field is pointing downward, the charge will accelerate downward and it'll arrive at point 2. And in this problem, we're ignoring gravity, so we're only interested in electric forces here. So forget about the fact that the charge has a mass. Just imagine this region of space is completely empty. There's no gravity. There's nothing here except for the electric field and the charge. And also in this part, ignore the fact that charges emit electromagnetic radiation as they accelerate in space. This is something that we can't deal with at this level in this course, and is given in much higher level courses. So for our case, we just have a charge that's accelerating in an electric field, and the only energies we're going to be looking at are the kinetic energy and the potential energy. So what is the work to go from point 1 to point 2 due to the electric force? It's integration from 1 to 2 f dot dr, and we know the relationship between work and potential difference between 2 points. You just multiply by the charge q. So let's define u initial minus u final to be q times v1 minus v2. So this, let's make it a definition, and we'll then identify in a while what this u initial and u final means. So if you put here u initial minus u final, and we still need to interpret what this u is, but this is what the relation we have now. And let's try to apply the work kinetic energy theorem. We know that the work due to the electric field, for the work kinetic energy theorem, what is the total work done? The total work done by all the forces, what is that equal to? Equal to the change in kinetic energy. So it should be the final kinetic energy minus the initial kinetic energy. So that means if you rearrange terms, you can see that you get k initial plus u initial is equal to k final plus u final. So this is a statement of conservation of energy. So this allows us to give meaning to the function u and to consider this u to be electric potential energy. So it's very similar to the gravitational potential energy, but it's now due to the electric force. So remember, in this part we're ignoring completely the fact that charges, when they accelerate, they emit electromagnetic waves. And this statement of conservation of energy ignores this fact completely. So here what we see is that the kinetic energy can be converted into potential energy as the charge moves from the top position to the low position. If it starts out at rest, for instance, then all the energy is potential, and then as it goes down, it gains kinetic energy and loses potential energy. So the potential energy of the system gets weak, gets less, but the total, the sum of these two, always remains the same.